Welcome to Quantum Computing Essentials Part 1, Lecture 7. Today, we'll be discussing about some very special matrices. And the matrices are the projector matrix, the projectors, then the reflectors, and the rotators, rotation matrices. Reflection matrices, the reflection matrices, and the rotation matrices. Okay, so in simple, I'm calling this matrices as projectors, the reflectors, and the rotators. So in the previous lecture, in lecture 6, we have discussed about the special matrices, unitary matrices, the orthogonal matrices, the normal matrices, symmetric and Hermitian matrices, TSD matrices, and condition for EVD and Cholesky decomposition. So first we'll be discussing about the these projectors, reflectors, and the rotators, some mathematical foundations for some n-dimensional system or n cross n metric space. And then we'll give certain examples for our two-dimensional system for simplicity. Okay. So first, let us start the elementary orthogonal projectors. Okay, elementary orthogonal projectors. So take a vector. Let's take a vector like this. Let U is a vector which belongs to certain C n cross 1. And if it is a quantum state, let get U. Okay, you can represent this as some other notation as well. So takes a vector U such that all the U, the norm of U equals 1. So you can consider a quantum state, and by quantum postulate, it can be a unit norm vector. There is a matrix of the form, a matrix, then a matrix of the form, a matrix of the form given by Q equals to the identity matrix minus the outer product of these state vectors. So you can denote like this. So this particular matrix is called the elementary orthogonal projector. This is called an elementary orthogonal projector, in short EOP. Okay, so let us also see that if this is not a quantum state vector, it is some arbitrary vector, and suppose u is not the norm of u is not equals to 1. So for any arbit u, for any u, okay, not necessarily it's a unit norm vector, it's some complex n cross n, then this elementary orthogonal projector will be the identity matrix minus the u into u star. Okay. It's some vector. You can take a under bar divided by its norm square. Okay, so you are just normalizing this divided by u square. So let us see the geometry here. Suppose that you have the vector u in some z direction or in some direction like this. So this is the vector u or the ket u, okay? And obviously uh, you can have a plane orthogonal to this like this. So this is a plane which is orthogonal to this particular state vector. So you can write it as the u parp that's perpendicular to the vector u. Okay. So it's a u parp plane, u parp plane. Okay. And there is certain vector. Say it's some vector. So take some other color so that we can represent it well. So assume there is some other vector x. Okay, x is some other vector. Say it is some kx. Okay, it's some vector. So obviously you can take the projection of this particular vector on this plane. Okay, so there is some other vector, this one, and you can also connect this as it is on the z plane. So you can also connect this to by some vector. So if you multiply this the orthogonal elementary basis with any arbitrary vector kx, then this particular vector will be q into kx, which will be actually equals to the identity minus ket u outer product with ket u, okay, and multiplied with kx. Okay. This kx can have some different norm. Okay, it should not be always like it's a unit vector. It's some arbitrary vector, and you can always take the projection of this kx on the u per plane orthogonal to this u, whatever be the vector that will connect origin to this particular point. Okay, so this particular vector will be the u into kx, and the other side, this particular on the u plane, on the vector u. So that particular part will be actually the identity minus u into kx. We'll see examples, okay, how it's a projector actually. Okay, so basically elementary orthogonal projector is that the word elementary means you are taking a unit norm vector u, typically a quantum state vector. If it is the case, then there is some orthogonal plane which is perpendicular to this u, and there is some arbitrary vector x. Okay, you can always that represent the arbitrary quantum state vector or some arbitrary vector on the plane of u part as well as on the plane of u. So if you take the projection on the u part plane, the connecting vector will be actually q into kx, and the norm of this will give you the distance from origin to the projection part, okay, this particular point. And if you take the projection of any arbitrary vector on the plane u, the effective vector will be I minus q into kx, okay, to that particular point here. Okay, say it is some p point, it is some r point. So p is already not taken, so p and r, like that. So by this way, you can represent any arbitrary uh, vector kx or quantum state x as the uh, quantum resolution or the vector resolution by vector resolution property given to the kx plus I minus u into kx. Okay, the part any arbitrary vector that you can resolve it on the perpendicular to u plane on and on the same u plane. So by this way you can represent any arbitrary quantum state vector. Okay, so this particular part is on the u plane, okay, which is parallel to u plane, you can say, kt, and this is perpendicular to u plane. Okay, so so let us take certain notes here. Point number one is that for vectors u and kx, for vectors u and x that is in the dimension n, okay, n cross 1, say, or n, you can write n cross 1, such that the norm of u is 1. If this is the case, okay, then I minus you can represent like this. Then I minus I am writing in gate notation as the state is actually 1. So I minus u outer product into the vector kx or some x arbitrary x. You can take it as some arbitrary x vector is the orthogonal projection of projection of the vector x on u per plane, right? On u per plane, uh, u per plane. Okay, and uh, secondly, the u star into the vector x, and if you take its mod, okay, it will represents the length of the orthogonal projection of orthogonal projection of the vector x on onto the one-dimensional space, onto the one-dimensional space spanned by uh, this norm u bar, or you can take the ket notation as well. These are two simple notes you can keep. Now we'll see the examples at the last of the lecture so that you can easily understand these things. Okay. Uh, so take some another notes as well in this part. Some more notes. For every non-zero vectors, for every non-zero vectors, u belongs to the Cn cross 1, the orthogonal projectors onto the span for the vector u and or uh, or better to write span of u perp r, and obviously it's better to write in this way, and span of u perp for obviously, yeah, the vector u shouldn't be uh, a zero vector. It's a shouldn't be a zero vector. Then the projector p for the span of u per u vector represented by pu should be equals to u star divided by u star u. Okay, u star u. Similarly, for u per span, in the span of u perp, the projectors will be just I minus eu, which equals to I minus u star divided by u star u means the outer product divided by the inner product of the vectors. Okay. So a very important note is that the elementary projectors are not isometries. Okay. In the last lecture, we have seen the isometries. The elementary vectors are not isometries as they are singular. Okay, as they are singular matrices. So next, we'll go to the matrix known as elementary reflectors. The second point is elementary reflectors. So obviously, as you remember, the reflection is what? So on a certain surface, some ray from an object comes to the plane, and if you have some orthogonal line on that particular plane, it will create the same angle of incident at the same angle of reflection. Then there will be a reflected wave, okay, from the surface. Similar phenomena is there, and you can have the mathematical equation as follows. So uh, for some vector u, and it should not be a zero vector, uh, the elementary reflector about, this is important, about u part. Okay, about u part, and thus u or u pub should belongs to c and cross one. Okay. So u pub is defined as R is reflector defined as I minus twice. This factor is very important. Twice. In the projection, we have seen it's the factor was 1. Here, the reflection, the factor is 2. Twice u star, the outer product of the vectors u divided by the inner product u star u. This is very important. And if u is a unit vector, say for example a quantum state, then your reflector will be I minus twice the outer product of u and u for get u norm equals to 1. Okay. This is the reflector. This is a very important operator in quantum. Projectors are also very important because suppose you have some unknown quantum state psi. So, and you don't know means the phase or some other information of this quantum state. So you do certain quantum evolution and try to reach uh, uh, try to get some information of the quantum state about either say the computational basis. Okay, get 0 and get 1. Okay. Ket1 and Ket0, or some Fourier basis or Hadamard basis, say plus and minus. Okay. So what you effectively do, you take the projection of this particular state on this basis or this particular basis. Okay. So how to take the projection? So you need the projection operators that should be multiplied on this particular quantum state vector, and you get the orthogonal projector vector, and after taking the modulus you get the value of that particular value, or effectively the probability amplitude of the quantum state about a particular basis. Okay, so this kind of examples we'll see. Okay, so now there is some names. Okay, this R is also known as, name of this R also known as AK, also known as householder transformation or the householder matrix. Householder matrix. Householder transformation matrix or householder matrix. Okay. So what effectively we are doing is that earlier what we were doing. So earlier we had some say this is some vector u. Maybe it's a unit vector here. You may take some arbitrary vector as well, and there is a plane, right? So which is the u bar plane. So this is the u bar plane. This is the u bar plane. Okay. So what earlier we did is that there is some arbitrary quantum state vector or some vector kx. Okay. So we were taking this vector projection on this plane and projection on this particular line or this particular plane. So you can take the projection over here. You can take the projection over here. So this particular thing was done using the multiplication with the cube. Right now you have the reflection. So if you want to take the reflection about this u per plane, so there should be this kind of vector, which if this is the incident angle, then this should be the reflected angle, and they should be same, right? So if you covered this much distance by the projection, so you should cover the another amount of distance, right, to get the reflected point. So this kind of projection you did using the outer product of u with u. Now you have to take the twice of the outer product of this particular thing. So so obviously you should multiply with an operator r with the state vector kx to reach this particular point, say x bar ket. Okay, so it is actually I minus twice the outer product of u into kx, right? So you effectively you get the result. Okay, the reflected result. Okay, and here we have taken u equals to the norm of u equals to one of the unit norm vector. So there are certain notes. Okay, so R if R is unitary, it's a unitary matrix, and Hermitian, this matrix R matrix, the reflection matrix is unitary, it's Hermitian matrix and involuntary. That's very important. Involuntary. That means R squared is equals to 1. I. Okay. So because R equals to Hermitian R star, right? Uh, and so if R square equals to I involuntary, so R equals to R star equals to the identity as R star, as R star, because it's unitary. So R star equals to R star R equals to I. Okay, this is the unitary property, and this is the involuntary property, and this is the Hermitian property. And if you combine all these things, so then basically we'll effectively get R equals to R star equals to I. Okay. So effectively we get R equals to R star equals to. So this is one particular case. Okay. So we'll continue this part, the rotation part. That is a very important part, and certain examples in the following. So especially the Gibbons rotation, which will help us to diagonalize a particular system, okay, together with this reflection and the projection thing. So thank you for this for joining this particular session, and we'll come very soon for the next lecture to be continued on the rotation and the examples of projections, rotation, and the reflection. Thank you very much.